Let us now see how we can evaluate integrals of functions of a real variable using the residue theorem. Okay, the first type that we are going to see is integrals of the following kind. Okay, let us call these integrals as j. So here the integrand is a function of sine theta and cos theta, where theta is a real variable. Okay, and what is f? F is not only a function of sine theta and cos theta, but more importantly it is a rational function of sine theta and cos theta, which is finite over the interval of integration. Okay, meaning you cannot take something like 1 upon cos, okay, which is not defined at 0. Okay, alright, or better, you also cannot take something like this, 1 upon cos theta minus 1 upon 2. Okay, this is not allowed, because if you let theta to be pi by 3, which is very well in the integrals, in the interval of integration 0 to 2 pi, the function becomes infinite. Okay, so it has to be a rational function of cos theta as well as sine theta, provided it is finite over the interval of integration, which is 0 to 2 pi. Okay, now we will be following the same procedure in all these problems, type 1 integrals. Okay, and that procedure is this: we will introduce a curve in the complex plane, okay, parameterized by a real variable theta, which takes the value, or which takes the values between 0 and 2 pi. Okay, so this is now the parameter theta, and the associated curve in the complex plane is the unit circle. We can take the unit circle. Okay, mod z equal to 1. This is the curve in the complex plane. Alright, now this means we can substitute z as r e to the power I theta, but because it is a unit circle, we can just say that z is e to the power I theta. Okay, now this substitution is by far the most important substitution in any of these problems. Okay, once you substitute this and take the derivative of both the sides with respect to, well, z, then RHS will have derivative 1. The derivative of the left hand side would be e to the power I theta into I into d theta by dz. Okay, yes, so we want d theta in terms of dz. So if you shift dz to the other side, it will be dz upon e to the power I theta into I, but e to the power I theta is z itself. Okay, so the differential d theta is now going to be dz upon I times z, with c being the unit circle, mod z equal to 1. Okay, remember we have done the exact opposite thing when we evaluated the integrals, when we did not know the residue theorem, even we did not know the Cauchy's integral formula or the Cauchy's integral theorem. Okay, there we brought in the parameter. Now we are doing the same thing in the reverse way. Okay, we are transforming the real integral into a complex integral. Okay, fine. So once we get the replacement for d theta, the differential d theta in terms of dz, or differential dz, it's now time to get the expressions for cos theta and sin theta in terms of z. Okay, it's very simple. Use the Euler's formula. Okay, e to the power I theta is cos of theta plus I into sin of theta. Okay, by eliminating sin theta, the formula for cos theta would be e to the power I theta plus e to the power minus I theta upon 2, or z plus 1 upon z divided by 2. Okay, same thing for sin theta. You have to eliminate cos theta from this. Sorry, I did not tell you the second one. E to the power minus I theta is cos theta minus I sin theta. Okay, so if you eliminate cos theta this time, Sine theta is going to be z minus 1 upon z upon 2i. Okay, don't forget iota here. It's going to be there. Okay, all right. So these three things, first d theta, second cos theta, and third sine theta. These three things, when expressed in terms of z and dz, allow us to evaluate this integral as a contour integral taken over the unit circle C in anti-clockwise sense, because that is how our parameter is increasing. Okay, fine. So let us now see problems based on this. Question 1. Evaluate the integral from 0 to 2 pi of the function. So this is our integrand. Sine squared theta upon 5 plus 4 sine theta. Okay. Now instead of sine squared theta, you may even have 1 minus cos squared theta. That's fine. Okay. But as far as possible, try to make it as simple. We'll try to keep it simple, and then let us now make the appropriate replacements. Okay. First, let us go to the denominator because it has only sine theta. So 5 plus 4 sine theta is now going to be 5 plus 4 into z minus 1 upon z divided by 2i. Okay, so this is what we got from the Euler's formula. Yes, this one. Z minus 1 upon z upon 2i, and write its square in the numerator, which is sine squared theta. Okay, z minus 1 upon z squared divided by 2i squared. Okay, last thing is the differential d theta, which is dz by iz, this one. Okay, so once we convert everything into z and dz, we are now set to apply the residue theorem. Okay, now you may get a bit complicated rational functions, but well, we have to now deal with them. Okay, so given the integral will be the contour integral along C taken in the anti-clockwise direction of the function z minus 1 upon z whole squared divided by 2i squared. Okay, so this will be z squared plus 1 upon z squared minus 2, a minus b bracket squared formula, into 1 upon square of 2 times I, which will be minus 4. Okay, so this is going to be the numerator. Don't forget that we have I times z in the denominator here, in addition to 5 plus 4 sine theta. Okay, so it is 5 plus 4 upon 2i, which is 2i, so it is 2i times z, and then minus sorry, okay, so let me just explain this. 4 upon 2i is actually minus 2i, isn't it? Because 4 upon 2 is 2 and 1 upon I is minus I. So it is going to be minus 2i multiplied by z minus 1 upon z. So the first term is going to be minus 2i z, and the second term, which is already having a negative sign, it will then become 2i into 1 upon z. Now please do these calculations carefully, because in the it is the denominator which is going to give us the poles. Okay, so even if the signs, one of the signs changes, you may be evaluating a different integral. Okay, fine. Alright, so the next thing that I have done is I have taken 1 upon minus 4 along with this I outside the integration process, okay, or outside the integration term. Okay, so it is going to be minus 1 upon 4i, let's keep it as it is, into the integral of numerator as it is z squared minus 2 plus 1 over z squared. And this time what I have done is I have multiplied the blue bracket by z. Which z? This one. Okay, don't forget it. Okay, so it will be 5z minus 2i z squared plus 2i. Alright. The next thing is you have to take, or I would say you have to multiply and divide by z squared. Okay, because you have 1 over z squared here. So if you do that, what will you get? It will be z to the power 4, yes, minus 2z squared, yes, and this will now be simply 1. Okay, but as a result of this, the denominator will also get multiplied by z squared, but don't multiply this quadratic expression by z squared, okay, because anyways we will be equating this denominator to 0, which will produce the poles. Okay, so it is z squared into the original denominator, 5z minus 2i z squared plus 2i. All right, now the numerator can further be simplified to z squared minus 1 the whole squared. Keep it as it is. And as I told you in our previous problems, whenever you are finding the poles or whenever you are factorizing the denominator, always make sure that the coefficient of z squared or the highest degree term is 1. Okay, in this case it is not, it is minus 2i, so take minus 2i common from the denominator. Okay, so as far as z squared is concerned, its coefficient is now 1. The constant term is 2i, you have taken minus 2i outside, so it will be minus 1. Okay, and the first degree term 5z divided by minus 2i. Okay, all right, now we can go to the process of finding the poles. Okay, first thing is, you note that there is this quadratic factor z squared, and when you equate this to 0, you will get a pole of order 2. Okay, our next job is to look for the roots of the equation z squared plus 5 upon minus 2i times z minus I equal to 0. Okay, so let's now do that. 1 upon I is minus I, so when it goes to the numerator, it will cancel the negative sign. So you'll get this equation now. Okay, you can get the roots on the calculator. Oh yeah, okay, so if the coefficients are complex or not real, then you can't solve them on the calculator. So you have to now apply the quadratic formula. Okay, z is equal to minus b, so minus 5 by 2i, plus or minus root of b squared, which is minus 25 by 4, minus 4ac, which will be plus 4 upon 2 or upon 2a. Simplify. Okay, minus 5 by 2i plus or minus, now this is going to be minus 25 plus 16 upon 4, which is minus 9 upon 4. Take the root, you'll get 3i by 2, right? Okay, now if you let the plus sign, if you consider the plus sign, then what will the numerator be? It is going to be minus I, denominator will be 2, so minus I by 2, that's the first root. If you let if you consider the negative sign, then it is going to be minus 4i upon 2, so minus 2i. Okay, and both these poles will be of order 1, or they are simple poles. Okay, now, well, we'll check whether our roots are correct. Take the product. Okay, what is the product of the roots? I squared is minus 1, minus into minus plus, 1 upon 2 into 2 is 1. Okay, so the product of the roots is negative 1. Is c by a negative 1? Yes, it is. Okay, now take the sum. Sum will be minus 5i by 2. Is it minus b by a? Yes, so always do this check. Okay, so the roots are correct. Now it's time to determine the location of the poles, the relative location with respect to the unit circle, okay, which is always the contour of integration in this type of problems. Alright, so we now need to determine how many of them lie inside. Mod z equal to 1, so clearly z equal to 0 lies inside. Mod 0 is 0, which is less than 1, and so does z equal to minus I by 2, because its mod is 1 upon 2, which is less than 1. Z equal to minus 2i will lie outside, because mod of minus 2i is 2, which is greater than 1, so it is farther away from the center. Okay, alright, so by the residue theorem, now we can say that the value of the integral of f of z with respect to z along the unit circle C is 2 pi I times the residue at 0 and the residue plus the residue at negative I upon 2. Okay, now let us go to z equal to 0. Okay, now this is of order 2, so we are required to find the first derivative. Okay, n is not 1, sorry, n is 2, or k is 2. Okay, k is 2. So the residue at this particular pole will be 1 upon k minus 1 factorial, which is 0 factorial, so there's no need, oh sorry, not 1 minus 1, 2 minus 1, which is 1 factorial, which is 1, so no need to consider that. So what I'll now do is I'll go to the function, okay, which one? This one, and I will multiply this function by z minus z naught to the power k, which is the term z squared. So z squared will now go. That is, our job is now to find the derivative of the rational function z squared minus 1 the whole square divided by this quadratic factor present in the bracket. Okay, yes, so apply the division rule, and always keep an eye on this. Okay, the moment you find that that term is going to be 0, there is no need to write the other term. Okay, apply the division rule. By division rule, the residue will be equal to derivative of the first function 4z cubed minus 4z, don't write denominator because this is going to be 0, okay, due to the first term, minus the numerator, which is this, into the derivative of the denominator, which is 2z plus 5 upon minus 2. Okay, fine, divided by the square of the denominator. Fine, let us substitute z equal to 0, the denominator will be 1. Yes, now go to the numerator. Okay, as I have already told you, there is no need to consider the first term because of this 4z cube minus 4z. Z is present in every term, each and every term, so 0. Okay, now what is the value of the numerator at 0? It will be again 1 because rest of the terms contain 0. Okay, 1 into, yes, now for this, the box bracket, derivative of the denominator, 2 times z, so 0, plus minus 5 by 2i. Okay, so this is going to be the numerator, 5 upon 2i, denominator is 1. Now the difficult part is over, the process of differentiating and getting the residue at 0, because it was not a simple pole, it was a pole of order 2. Now, is it possible to find the residue at z equal to minus I by 2? Yes, this is a simple pole, or n1, or k is 1. Okay, so the residue will be the value of that function which you get after multiplying the original integrand by z plus I by 2. Okay, so again let us go back to that green integrand. Okay, we have already factorized this into, okay, what were the roots? Minus I by 2 and minus 2i. Okay, so the factors will be z plus 2i into z plus I by 2. Okay, so we will now not consider the factor z plus I by 2 because we are multiplying the function by that. Okay, so it will be numerator as it is, and in the denominator we now have z squared. Okay, in the first thing it was not there because we were finding residue at 0. So z squared into z plus 2i, so this time z minus z plus iota by 2 will not be there, this one, and it is a pole of order 1 or a simple pole. We'll just put z equal to minus I by 2 there. Okay, fine, so this is how we get the residue at minus I by 2. If you put z equal to negative I by 2 in the numerator and in the denominator, of course, you will get the value as 25 upon 6i. And therefore the real integral is equal to 2 pi I times the summation of residues at those poles which are inside C, but let's also not forget these things. Okay, minus 1 upon 4i and this minus 2i in the denominator. Okay, so I have taken them at the very end, minus 1 upon 4i which is already there and 1 upon minus 2i, okay, into 2 pi I times the sum of the residues. This is there. Okay, now minus 1 upon 4i into 1 upon minus 2i, minus minus plus 4 into 2 8, I squared minus 1, so minus 8, 2 pi I as it is, add them up, you'll get 5i upon 3, I squared will again be minus 1 which will cancel this, and eventually you'll get 10 upon 24 or 5 pi by 12. Okay, now one good thing which I like about these problems is you can always verify your answer on calculator. Okay, so let us do that for this problem. So one thing that you need to make sure while calculating integrals on calculator is that if your integrand has a trigonometric function, make sure that your calculator is in the radian mode. Okay, you can see that R here. Okay, now we will input everything. Integral, let's first input the denominator, 5 plus 4 into sine of theta. So let us take x because x is the variable of integration now. Okay, now the numerator, it is sine theta squared. So let me first take the square and inside the bracket let us write down sine x. Okay, so this doesn't understand sine squared x, okay, as per my knowledge. So you first type sine x and then put a bracket and then square it. Let's now get the limits. Yes, lower limit 0, upper limit 2 times pi. The value is 1.30899. Okay, now what was the value that we had got? 5 pi by 12. So let us now evaluate 5 pi by 12. Which is also 1.30899. Well, approximation. Okay, so both these values match, the value of the integral and the value of 5 pi by 12. Hence our answer is correct. Let us now go to a slightly complicated problem. Question 2. Let a be any real number between 0 and 1. Evaluate the integral of the function 1 upon 1 minus 2a cos theta plus a squared with respect to theta, and the limits on theta are 0 to 2 pi. Okay, so this time we have cos theta in our integrand, okay, which is 1 upon 1 minus 2a cos theta plus a squared. So you have to now bring in the formula for cos theta. We all know that cos theta is e to the power I theta plus e to the power minus I theta upon 2, and here e to the power I theta is z. Okay, so in every such problem you have to show all these three things. Okay, well, now third thing is not required to be shown because sine theta is not a part of our integrand. Okay, but you have to show that d theta is dz upon iz and cos theta is z plus 1 upon z upon 2. So having done that, what will we get? Let's go to the integrand first and then let's go to the differential d theta. Okay, replace cos theta by z plus 1 upon z upon 2, cancel 2 and multiply z plus 1 upon z by minus a. Okay, so you'll get 1 minus az minus a upon z plus a squared. Okay, now don't do anything to this because there is an additional z present in the denominator due to the differential d theta. Okay, this is dz upon I times z. Yes, and therefore the given integrand will now get transformed to a contour integral. Well, I shouldn't have said integrand, I should have just said integral. Okay, so the given integral will now get transformed to a contour integral evaluated along the contour C, which is the unit circle, mod z equal to 1, due to the substitution z equal to e to the power I theta. Okay, fine. So this is the integrand and this is the differential. Take I common from the denominator, this one, put it here, okay, into the integral of 1 upon, multiply everything by the remaining term here, that is z. So it will be z minus az squared minus a plus a squared z. Okay, again you make sure that the coefficient of the largest power of z in the denominator is 1. So take minus a outside. Okay, so once you take minus a outside, you will get 1 upon minus ai multiplied by the integral of z squared, the first term as it is. Now there are actually two terms containing z. Because you have taken minus a common, divide z into a squared plus 1 by minus a, and then the constant term is minus a, and you have taken it outside, so plus 1. Now this is a quadratic equation, a quadratic expression, okay, the one in the denominator. So this function, being a rational function, is now going to have only two roots because it is a quadratic expression. Okay, solve it. Z squared minus a squared plus 1 upon a times z plus 1 equal to 0. So after solving the quadratic equation, the roots are z equal to a and z equal to 1 upon a. Okay, addition a plus 1 upon a, is it minus b by a? Yes. And product z1 into z2, which will be 1. 1 is the reciprocal of the other, of course, and c by a is 1. Okay, so now the roots are correct. Okay, now let us determine the relative location. Note that a is less than 1 but positive. Okay, so absolute value of a will be less than 1, so this has to be inside c. Okay, and 1 upon a will obviously then be a real number greater than 1, so this will lie outside. Okay, so by the residue theorem we are required to evaluate the residue of the residue at z equal to a, because that is the only zero or singularity which lies inside. Okay, inside C. And to do this we will go back to the integrand, okay, the factorized version, and we will only consider that factor which doesn't correspond to a, okay, which is z minus 1 upon a. Yes, okay, so if you substitute it, you will get 1 upon a minus 1 upon a. Okay, remember this is a pole of order 1, both of them. Alright, so to calculate the residue we multiply the original function by that factor. Okay, and here because f of z itself is 1 upon z minus 1 upon a into z minus a, it will just be z minus 1 upon a. Okay, the other factor will get cancelled due to this. So it will be 1 upon a minus 1 upon a, substitute z equal to a there. So a squared minus 1 in the denominator, a in the numerator. So the real integral will be 2 pi I times the sum of the residues, but there is only one number there, one residue, a upon a squared minus 1. Let's also not forget that we have a factor outside, that is 1 upon minus ai. So let us multiply our answer by 1 upon minus ai. This will eventually lead to the cancellation of I. So it is 2 pi, okay, and also a will get cancelled. So it's 2 pi upon minus a squared minus 1, or 2 pi upon 1 minus a squared. Fine. So see, now how can you verify this on the calculator? Because you have the parameter a here For this, you take any convenient value of a, provided it satisfies the constraint that it lies between 0 and 1. So let's take a as 3 by 4. So what will the integral now? 2 pi upon 1 minus 9 by 16, 16 minus 9, 7. So it will be 32 pi by 7. Okay, now let us now see whether we get the same value on calculator. So we have, okay, let's not disturb the limits. Let's only go to the integrand. What we have in the denominator is now 1 minus 2 into 3 by 4 into cos x plus 9 upon 16, which is the square of a, the value of a that we have chosen, and the numerator is 1. Okay, so the value that the calculator has produced is 14.361. Now let us go to 32 pi by 7. $14.361. Well, there is a minor difference. 14.3615, 14.3614. Okay, but nonetheless the answer is correct. Okay, let's try with a different value maybe. Okay, so let's take 1 by 2 and see what value we get. Okay, so here we won't have 9 by 16. Now we will have 1 upon 2, or okay, sorry, 1 upon 4. We are squaring it, so 0.25. And here instead of 3 by 4 we'll have only 1 by 2, so let's not take it. Okay, 1 by 2 into 1 is 1 by 2 into 2 is 1. Okay, so 1 minus cos x. Now let's calculate this. 8.377. Okay, so for a equal to 1 upon 2, what is the value? 2 pi upon 1 minus 1 by 4. 8 pi by 3, or 8.377, which matches with this value, 8.3778. Okay, so that's how you can even verify the values of such integrals. Okay, fine.